everyone, it's Miss Silverthorne. These are the notes that we started in class and in your packet. If you happen to have your packet, these notes are pages 11 through 21. We already did the first couple of pages, but just in case you don't have your packet or in case you need to review or you missed a day, I'm going to start from the very beginning of these notes. So if you remember when I was talking in class that we are talking about geological history and we're breaking it up into three main sections. So we have relative dating, absolute dating, and then the actual geological timeline is what we're going to be looking at. For these notes here from pages 11 through 21, we're just going to be looking at the relative age. So how do we determine how long ago events on Earth occurred? We do that through the study of interpretation of Earth's past, which we call geologic history. So again, like I mentioned, we have two different time scales, relative age and absolute age. Relative age is the age of rocks or events compared to the age of other rocks or events. So an example of this would be saying I am a teenager. So without knowing your exact age, you should be able to look at somebody and know, hey, these kids are younger than me, or these people are older than me, just by looking at them. You kind of already can compare and contrast your age to someone else. You could even do these things with like food, right? You could probably look at some food and be like, oh, this food is old and not good for you. That's called relative age. The other is absolute age, which is where you do know the exact age. And in our case, it's the exact age of a rock, object, or event in years. So instead of saying, oh, I'm a teenager, you would be saying, oh, I am 16 years old, or I'm 14 years old, or however old you are. So again, that's the difference between relative age and absolute age. Leading us into some definitions, we use three main principles to guide us in figuring out the relative age of things. The first one is uniformitarianism, which is the geological processes that took place in the past are generally similar to those that take place now, meaning that the best way to understand how our Earth has been shaped is by looking at how is our Earth being shaped now. So the idea is that how mountains are formed now, the processes that form mountains that we can see happening now is how mountains would have formed, thousands of years ago, millions of years ago. Same thing with like volcanoes, or we talked about oceanic trenches. Any of those that formed, or the processes that formed those hundreds, thousands, millions of years ago are the same processes that are being used today. And that, again, this is called uniformitarianism, so it's all uniform. The second principle is called the principle of original horizon. I can never say this word. Horizontality, maybe? Okay, so this means that sediments are deposited in horizontal layers that are parallel to the surface that they are deposited on. So in this case, looking at the image, we have deposition happening. Here, let me see if I can use a laser pointer. So we have a deposition, assuming that things are going to deposit parallel. So think of when you were like shake a bottle with maybe dirt in it, and all the dirt is going to settle at the bottom, and it's going to settle in layers. That's the same idea. We're just giving it a name this time. Okay. What this means is that if we find layers that are not parallel, that are not horizontal, that means some type of plate tectonic activity had to have occurred. Something had to have happened to cause those layers to not be horizontal, which means they either tilted or folded, again, due to tectonic activity. Okay, the last principle that we're going to talk about is the principle of superposition. This means that in undisturbed layers, the oldest layer on the bottom, or the layer on the bottom, so this layer here, is older than the layer on top, which would be younger. So think about if you're stacking books on top of each other, right? So the book that you put on the bottom, has been there longer than the book that you put on top. The same idea applies to rock layers. Now, if there's been some plate tectonic activity that have, again, forced things to not be parallel, this rule may not necessarily apply, which we will talk about later on. So here is an example of principle of original horizontally and superposition is that, the cutter at the bottom would be the oldest, and then the Compton limestone on top would have to be younger. Here's just more real-world example of the recording of layers that we can see. Okay, now those are the three principles. Again, uniformitarianism, the principle of original horizontality, which I can never say, and superposition. So using those three, those are what's supposed to have happened. But obviously, there's our exceptions. These next couple of things where I'm going to talk about are the disturbances that you would see in these rock layers. The first disturbance is igneous intrusions and extrusions. So an intrusion, think in, right here, in means inside the earth, ex meaning it's exited the earth. So an intrusion is when the magma has squeezed up into the upper crust, but hasn't quite reached the surface, and then it goes and it cools and forms hard rock. Okay, and extrusions means it's actually exited and traveled outside to the top surface of the crust, and then it'll eventually cool and harden into rock. That's why you see a difference in here. So this one's, again, an intrusion. This section here, the sandstone, was there when the intrusion happened. And the extrusion, because it exited the earth, and then it cooled, and then the sandstone was deposited after the extrusion. Okay, erosion, which is the carrying away of weathered rock, is almost always due to water. Not always, but the majority of the time it is due to water. In this case, you can see we have deposition. It's been uplifted, which means it's been pushed up out of the crust. And then due to water, we have weathering, which creates this kind of wavy formation. Okay, and then we have, again, more water that deposits more sediment. And this here is why you get that wavy. That wavy line means it's been weathered. And we call that wavy line an unconformity. It often results in a gap in the rock record caused by erosion. And again, that's what that wavy line means, is that something's been eroded. We're missing some record of the rock record. Okay, let me go back. This is when you push two pieces of rock together, they're coming together, and eventually they're going to become bent or warped, and it kind of creates this wavy formation. Tilting is when, again, due to plate tectonic activity, we see that the normally very horizontal parallel layers are now going to be at an angle. And this is due, again, to plate tectonic activity. So here you can see in this real image, this has almost been tilted at a 90-degree angle. So instead of these lines here being parallel, they are now vertical. And that's due to plate tectonic activity. It looks like these might be some mountains here. So it looks like it has to do with two plate tectonics coming together. Okay, faulting. The most famous fault is the San Andreas Fault in California. So due to earthquake activity or plate tectonic activity, it's when a crack has formed due to a weakness in the Earth's crust at that location. And the faults are usually represented by a line such as this over here. And that's because it's also to show that one is moving up and one is moving down. Okay. Just to show you some animation, you should have seen this when I know I showed this in class. If I can get this to turn back to being a pointer. Let me see if I can get this. I'm hoping this still records. Okay, so if you watch this animation, it cuts through you can see how we have the layers of sediment piling up. Must be younger. So in order for something to cut through it, so that's the deposit through it if it was there in the first magma that's cooled, right? So you can't cut through a piece of like tectonic activity, erosion. Okay? If the cake wasn't already there, so when we were to cut through a piece of cake. Okay, and then we have an unconformity. You'd have to see those layers, right? Those layers, if you did a layer cake, would have to be there. If they weren't there, you can't cut through it. It's kind of the same idea. You saw that. Okay. If not, you can just copy over here to that link. What happened last? Okay. Okay. In these images here, what happened last should be, I want to say, I guess, A, right? So we have here, you can see this erosion, okay, that you don't see in these other pictures, which means this erosion had to have happened last, which means it's the youngest. Okay, E happened next. Okay, we have this extrusion. Okay, so now we want to look for what happens before E. Okay, and that would be D. Okay, then moving on to C, you can see that we have this fault. Okay, and before C should be F, right? Because now we have this tilting, this waviness happening, this folding. And then the first thing that always happens is we get the parallel lines. So this is the parallel deposition of sediment. Okay, I'm not going to, because I don't think it's recording it, so if you want to watch the animation, I highly recommend it. It's really good, and it can shows you just how complicated this is. All you have to do is copy the link to watch it, or type it in to your web browser. Okay, so using all of this, how can we interpret it to determine the order of events and what these events are? So we're going to be using events such as deposition, erosion, igneous intrusion, the folding, tilting, and the faulting. So looking at this, we want to go with what happened last. Well, this here, this line, because it cut through all of the layers, means all of these layers had to be there first. So that means they're older than F. And when we have a cut through like this, it's a fault. So fault F happened last. And just due to the superposition, the principle of superposition, these are all depositions. They are all parallel. So it should be deposition A, deposition B, deposition C, and then finally deposition D. Right? It's very similar, except you don't have deposition D. The other difference is these lines. So on the other one, B didn't have lines on top. And what that means, when there's lines all around something like this, in the case B, that means it's an intrusion, which means A had to be there first. Since it had to be there first, it has to be older than B. So the youngest part of this outcrop is igneous intrusion B. And then we have deposition of A and deposition of C, because you want to go from top to bottom. The top is always going to be the youngest. Like this, you see how this is flat? Okay, that means no erosion occurred. But in this, we have a wavy line, which means we have erosion happening. And here, okay, this indicates an intrusion. We also have some tilting. This is at an angle. And then finally, we would have D, C, B, A as in your depositions. So we have a lot going on in this picture. The last one's going to be the erosion, because we have the wavy line. Then we have the intrusion. Okay. Then we should have the tilting. Okay, because all 4 layers are tilted. And then the rest should all be your deposition. So deposition D, deposition C, deposition B, deposition A. Okay, another one. So again, we want to look at what we all have. Here we have a fold, or not fold, I apologize, a fault. Okay, we have an intrusion, and we know it's an intrusion because we have all those lines are all the way around it. And then we have the deposition of these layers. Okay, now to look really, really closely, X, okay, let me see. So the intrusion of E, because if E was there, then that line XY would have gone through E. Then we have fault XY, and then we should have our depositions of A, B, C, D. Okay. Now we want to know what the possible age of this igneous rock here is. So we know that the igneous rock, okay, cut through 34.3 million years, 28.0 million years, 24.2 million years. So that means it has to be younger than 24.2 million years because it cut through all of these. But it didn't cut through the 1.6 million year rock, which means it has to be older than that. So our age range for the intrusion is between 1.6 and 24.2, which they said 1.7 and 24.1. I would just stick with 1.6 and 24.2. Okay, so what does correlate? Just some vocab, it means to match. We're able to match rocks and geological events in one location with rocks and geological events in other locations. So sometimes due to plate tectonic activity, we can have a separation of rocks. So we can have formations in different locations, but we're able to correlate them. We're able to match them, and that's what we're going to do for the next couple of slides. So here is an outcrop, and you can see here in this case a river has created distance. It's eroded this into a valley, and so we can correlate this side ABC to what's happening onto the other side of the valley of ABC. Okay, so we have something called walking the outcrop. It means matching nearby rock layers that appear to be the same type and thickness. An outcrop is the actual surface of exposed bedrock. So it's what we can physically see because it's been exposed to the eye. So the Grand Canyon is an excellent example of this. If you can Google images of the Grand Canyon, and you can go in and you can see all of the layers due to the erosion of the river, and you can match up the layers of what's on one side of the canyon to what's on the other side of the canyon. Okay, here is a outcrop or a diagram of the layers. You can see here, even though there's a massive gap here, okay, we can see that this layer here is the same as this layer over here. Okay, so we want to correlate the layers. We're going to draw an arrow from outcrop A to the outcrop B. So starting with at the top, okay, we can notice that these layers here that are dashed should match over on outcrop B, these layers. So there's a matching correlation here. So we can draw those lines. We notice that the brick layer here, okay, we also have a brick layer over here. So we can draw lines from here to here, and then here to here. And then finally, we have another dashed layer of 2 rocks on both sides of our outcrops, and so we can draw matching arrows here. So you should notice that we are missing this layer here. This dotted layer is not over on this side. What could be a cause for this? Most likely it's going to be erosion, which is also why you see a wavy line over here, because if you remember, we represent erosion with wavy lines. Okay, so besides looking at this, what we're looking at is that scientists look at the color of the rock, so you can notice how there's uniform color here, and then you go up a layer, this color throughout this canyon at this layer is kind of the same. We also can test the composition. So what is the rock made of? Is it sandstone? Is it igneous? Is it metamorphic? So this one can get a little bit more complicated. So we're going to start with matching what happens to X and Y. Okay. If you notice, first we're going to do from the brick to the brick. Okay. Then draw an arrow from, this is conglomerates. We have a conglomerate over here, so we can match those up. Okay, the red sandstone, okay, matches with this red sandstone over here. Our black shale, we have black shale here. And finally, we have tan limestone and tan limestone. So then you notice we haven't matched these two at the bottom, and we haven't matched these two at the top. Okay, but we can notice that these two are matched in that way. So now if we go over between Y and Z, so we should notice that there's a brown siltstone here and brown siltstone here, so there should be, am I able to draw on this? Let me see. So there's a match from here to here, a match from gray limestone to gray limestone. Okay, we have some red sandstone and red sandstone, so we have a match here. We have black shale and black shale, so we have, again, another, I'm drawing this really bad, from there to there. And then we have this tan limestone to this tan limestone. So you should notice as well, let me change here, that we have this wavy line, right? We didn't account for this conglomerate, and that's because over here we have a wavy line. That means this has been eroded in this location. Okay? So I'm going to erase and have it drawn all nicely for us. Okay? Now we're going to do, so I'm going to go back. Now if we want to do from X to Z, it gets, I don't like it's a little bit more icky looking because you already have so much written on here. So you should know you have gray limestone, and this gray limestone matches to this one. We have red sandstone. So this red sandstone matches to this red sandstone. Black shale to black shale. Tan limestone to tan limestone, again here, and then this green shale to this green shale. Okay, so again, this conglomerate here has been weathered over here. Okay, and then so I'm going to erase my work, and you can see these arrows. So we know that all of these, even though they're in different locations, they have seen very similar geological layers are missing due to an unconformity. We match the layers, and I've already mentioned it multiple times. But the thing that is missing is this unconformity, which is also represented by a wavy line. So the conglomerate is missing. Okay, which rock layer is the oldest? So we should know from top to bottom. Okay, so we know it should be one of these at the bottom. Well, the green shale over here matches this one. So, but we have the gray siltstone or the tar limestone. and it's the gray siltstone is the oldest. Okay, which one is the youngest? Well, we're looking at the top here. So it should be one of these three layers. So the great limestone, the glacial deposits, or the brown siltstone. Okay, well, we know the gray limestone here got the brown siltstone. So the brown siltstone was done last. Okay, but the brown siltstone over here has the glacial deposits. So the glacial deposits should be last. So you start with one gray limestone, which matches over here, which shows that the brown siltstone is younger. But if we go back over here, the brown siltstone has something on it. Okay. So we can also use some other things such as volcano eruption. So volcanoes, especially if they're big enough, right? Like things like Krakatoa were massive. We can use those that volcanic activity to also help correlate outcrops because they do leave a layer of ash. Okay, this is very effective because it does represent that it took place rapidly, covered a large area, and it happened at a very specific point in time, right? Eruptions happen maybe over a couple of days, but it's not like where the big eruptions are happening over months or even years. So because they're happening at a very specific point in time, we can use this information to help correlate outcrops and figure out the relative age of things. So here we have volcanic ash, okay, and we can use that over here to determine where's Mount St. Helen. So due to wind patterns, when Mount St. Helen erupted in 1980, we had a path of that ash due to the wind that deposited this layer, okay. And so if we were to be able to dig down into certain locations up to, let's see, that's 30 years ago now. Oh God, that's 40 years. So 40 years ago when Mount St. Helen erupted, we can dig down, we would see this volcanic ash in this region that you see here. If you can watch this video. It's really good. Pompeii is an interesting geological event and the effect that it had on people. So you can just Google this, or I'm not sorry, Google it, but copy and click on this link. So what else do they use? They also use something called index fossils. These are fossils of organisms that lived over a very, very wide geographic area for a very short time. So wide area geographically, but short period of time. Okay, those are the two key things. We can use these fossils to be index fossils. So if it was over a long period of time, that's not very useful to us. It has to be a short period of time. So looking at these, we have fossils in each of these outcrops. We can, which fossil appears to be the best index fossil in this diagram below. So we want one that appears in the most, is the first thing that we could look at. So we have this like seashell, it's in all four. Okay, so that might be useful. We have, and it's only in one time period. This one right here that kind of looks like a butterfly to me. It's also in all four, but in outcrop 2, it's in 3 time periods. So that's not really that useful to us. Because remember, we want short time. If we look at this one here, I believe this one's a trilobite is what they're called. Again, they're in all 4, but they're in multiple time periods. Here, they had even skipped a time, or skipped a layer. It's in this one and then up in this one. And then the last fossil is this rod-looking one. It's not in all 4, so that's not useful to us. So the one that should be most useful is this seashell-looking one. Okay, so because it's in the second layer from the top, and it's only in this layer, and because it's in every column, that makes it very useful to us. Okay, so which letter is the best index fossil? Well, let's start with A. A is in all three, but A is also in, looks like every layer, right? It's in layer this one, it's in this one, it's in the third one, and it's in the bottom one. So I would say no to A. So let's go to B. B is in all three. Okay. But it's in 1, 2, it's in 3 layers. It's not in the 4th layer or the top layer. Okay. C is in all three. But C is confined to only this rock layer. So I would say C is your best index fossil, right? Because again, it's only confined to this layer. Okay. We want to know which one has the best index fossil. So let's see, X, Y, W, X, Y, Z. Let's start with W. W, yep, it's in all three. Let's see if it's in more than one layer. One layer, going down, one layer, one layer. So I would say our answer should be, without going any further, it should be W. Okay, this map shows a distribution of ash across the United States as a result of the Mount St. Helens eruption. Volcanic ash deposits such as these are usually excellent geological time markers because they occur at regular time intervals, spread over a large area in a short amount of time, represent a time gap in the rock record, contain index fossils. Well, it's definitely not index fossils, and it doesn't represent a time gap. Okay, the reason they are so good is because they spread over a large area in a short amount of time. Because remember, Mount St. Helens volcanoes don't normally erupt in regular intervals. So B would be your best answer.